Okay, so today Francesca and I are going to be talking about the most supermassive black holes in the universe and their environments, what they do to their environments, really. So first of all, what is a black hole? On the right-hand side here, I have an artist's impression of what the immediate environment of a black hole might look like, what we think it looks like. But what exactly is it? It's extremely dense matter that is so dense that nothing can beat the gravity of that matter, so that it continues to collapse forever. It's just a runaway collapse. So no equilibrium is possible. So why is no equilibrium possible? Let's think for a minute about equilibrium. You're all sitting on your chairs here in equilibrium. You might not have thought about that before, but in fact you are. The force of gravity of the Earth is pulling down on you, and the chair is holding you up against that gravity. Now, if you just think for a minute about if you sat on a less substantial chair, perhaps one that looks like a chair but is made of cardboard, when you sit on it, the cardboard isn't going to be strong enough, and so gravity will win for a little bit of time until you hit the floor. And the floor, of course, is strong enough to hold you up. So that's what happens when you're not in equilibrium. Our sun is in equilibrium as well. It's rather large compared with the Earth. The force of gravity is much stronger, and it holds it together. That force of gravity is balanced by the radiation pressure from all those light photons and heat photons that are trying to get out, having been generated in the center of the sun. So the balance between the gravity and the radiation pressure keep the sun in equilibrium for billions of years, as long as the fusion is going on in the middle. Now, once a source gets as big as a black hole, radiation pressure just isn't strong enough to balance the gravitational force. And in fact, nothing can balance it, not even the force between the nucleons in an atom, which does balance for a neutron star. If it gets too big for that, then you have a black hole, and it just collapses forever. So why is it black? As you can see in the middle here, it's black. In astronomy, we like to call things the way they look. So instead of having some complicated Latin name that you're never going to be able to remember, if it looks like a hole and it's black, we call it a black hole. If it's big and red and it's a star, we'll call it a red giant star. So you can tell what something looks like by what we call it. But why is it black? That is because not even light can move fast enough for it to escape from it once it's inside what we call the event horizon. Now, every body has an event horizon. The event horizon for the Earth would be about 1 centimeter across. So if you can imagine squashing the Earth so much that it could fit into 1 centimeter, you'd have a black hole that would have to be smaller than 1 centimeter, and it would be 1 centimeter across. So a lot smaller than the black holes I'm going to show you tonight. And in order for a rocket to escape from the Earth, when it's its normal size now, it has to be going quite fast in order to escape from the Earth's gravity. And that's the escape velocity. It's actually about 8 miles per second, about 50 times the speed of an aeroplane is the minimum to escape from the Earth's gravity. So around a black hole, once you get inside that event horizon, not even light can go fast enough to escape. So therefore, we don't see anything inside of that. So if they're black and they're a hole, how can we see them? That's a very good question. In fact, there are probably quite a few black holes out there that are just sitting in the middle of nowhere and we don't see them. However, because the force of gravity is so strong, and there's usually quite a bit of material around, the material will tend to fall in to the black hole. It'll spin around, a bit like the water in your bathtub when it's falling down the hole. It'll spin around the black hole as it tries to fall in under the force of the gravity of the black hole. And actually, because there's quite a lot of matter that's trying to fall in, it gets very hot. It rubs against, one atom rubs against the next, and will get hot rather like your hands get hot when you're rubbing them together. And it'll get so hot that we have thermal emission coming from it. So think about your barbecue coals. When you first light them, they're red. They're not very warm. As they get hotter, they get white hot, and then you can cook your hamburger on them. So this is called an accretion disk, the material that's spiraling around the black hole. gets hot enough that we get light, like you would from a barbecue. And actually even hotter. We even get thermal X-rays from an accretion disk around a black hole. So the way we see them is by the things around them, not by them themselves, and the effect that they have on those things. So let's have a look first at stellar mass black holes. These are black holes that have a mass that have to be more than about 3 times the mass of the sun to be able to form a black hole. They can be formed when a big old star blows up, for example, and you end up with a remnant that's bigger than 3 times the mass of the sun. We can see them very well if they're in a binary system. And here on the right, I have an artist's impression of what a binary system with a black hole in it might look like. So right in the center of this region here, you've got a black hole. You don't see it because it's surrounded by a very bright accretion disk. And the way that accretion disk is fed is from material from the other star, the companion star, which is physically much bigger than this accretion disk, but it's much less massive. So the accretion disk wins, and it sucks material off this star. And the material gets very, very hot, and we get emission from this. We also get jets. Well, I'll be talking about those in a minute. Down in the bottom left here is a schematic of what might be going on right in the central regions of the accretion disk. So here's the disk, the material moving around. And then it stops at some point, which is called the innermost stable orbit. And what that means is that matter that's sitting here can actually stay there in a stable orbit, like the moon moving around the Earth, for quite a while. And eventually, some of it, as it jostles against other pieces of matter, will fall in. And then it'll fall in extremely quickly. And the tidal forces will pull it apart, so it'll get very hot. And eventually, it'll cross the event horizon, and the black hole will just grow a little bit more. But as it's falling in, you get a very bright burst of light coming from that matter. So these sources tend to be, these binary stars tend to be very bright. They're X-ray sources. You see the X-rays from the accretion disk. And they're variable. They tend to have bursts as matter falls in. So that's one of the ways we know where black holes are, is to look for binary stars. There are a couple of properties of a black hole which I'd like you to remember tonight. The 2 most important ones are the mass, of course, because that determines the gravitational force, and the spin of the black hole. Now, we've talked about the accretion disk, which spins around the black hole as it's falling in. The black hole itself could also spin. And in fact, if you imagine just a clump of gas falling in, it has angular momentum. It's very hard to lose that angular momentum completely. So some of it will be transferred to the black hole. Now, the difference between the two is if this black hole has no spin, the event horizon is here, the innermost stable orbit is further away than that. When you have a black hole that has spin, the matter can actually be stable much closer into the black hole. The event horizon is somewhat smaller. So those are the 2 most important parameters that tell you what effect a black hole will have on its surroundings. So now let's take a big step up to galaxy-sized black holes, the supermassive black holes, SMBH for short. And these form not from a star blowing up, but from they form in the centers of galaxies in the early universe. As galaxies form, some of the matter falls down into the middle and forms a black hole. And here on the right-hand side, I have a picture of a beautiful galaxy, which looks actually quite like our own. It's a spiral galaxy. In the center, there's a fairly bright source here, which is a black hole with an accretion disk around it. Now, this black hole is somewhere between 1 million and 1 billion times the mass of the sun, so way, way bigger than the stellar mass ones that were just a few times the mass of the sun. And the size, the event horizon for this kind of black hole, is about the size of our solar system, which might seem very big to us, but compared with the size of the galaxy, it's really tiny. And if you actually figure out how big this is compared with the size of this whole galaxy, it's something like a pin, this head of a pin, in 2/3 of the area of the United States. So it's very, very small. However, its mass is only about 1% of the total mass of the galaxy. So in terms of the mass, it has a much larger proportion of the mass of that galaxy than its size would have you believe. And the supermassive black hole continues to grow as the universe progresses, as it accretes material. And the center, as we've already looked at, has an accretion disk with a black hole in the middle. and there's a jet coming out from that one. So let's have a bit of a closer look at the central regions, the accretion disk here. This is looking from above, so it looks like a circle, like looking at a plate from above. And as we know, the material is spiraling in. I think I've been holding this down too much. It's not working. It gets very, very hot. It gets so hot and so bright, the accretion disk in the middle of a galaxy, because there's so much matter there, that it can outshine the 10 billion stars in that host galaxy. So that if you move it to a large distance, all you see is that bright center. You don't see the stars around it anymore. And at that time, when it's that bright, we call it a quasar. It's also hottest near the center. So you've got the white hot and blue hot down here in the middle. That's where the optical light comes from. Further out, you've got cooler matter, which is more heat type of radiation than light type of radiation coming from the edges. Now, if you turn it on its side, because it's a disk, it looks something like this. You actually no longer see the optical light. Your eyes can no longer see this. You still see the X-rays because they can penetrate through the disk, just like, I mean, this is why we have X-rays at the doctors. The X-rays can actually penetrate through a lot of matter. So X-rays are actually the best way to look for these quasars out in the universe, because you always see X-rays at whatever orientation the quasar is to you. So they're the sort of most important thing to look for. Let's see. The black hole grows, as I said, as matter falls in. But immediately around a black hole, it's quite chaotic. There's a lot of material trying to get in. It's a bit like observatory night here, actually. A lot of people trying to get in. And some of them don't manage to get in and actually get bounced out. So we get jets and winds coming off. They're not actually coming out of the black hole. They're coming from around the black hole. They can't get in, they bounce, and they come out. And so I'm going to look at some of those structures now. Here are some artist impressions of what they might look like. This is similar to the one I just showed you. There's an accretion disk here. You can only see the optical light, rather like you see the light from a closed door, just coming around the edges here. And then there's a jet. That's a polar jet that comes out from the poles of the accretion disk. And here, with a slightly different angle, you can now see the accretion disk with the black hole and the jet coming out perpendicular to the disk. This jet actually has these spirals around it, and that indicates that, in fact, and I'll tell you a bit more about this, the emission from this jet is from electrons spiraling around a magnetic field. So that's supposed to indicate that in that artist's impression. On the bottom right, there's a schematic of the structures we already know about. There's one new thing in here. The X-ray source is actually not as flattened as the rest of the disk. So this white area is where the X-ray is coming from. Plus, just to note that since they rotate, if you look at this side of the disk, it might be coming towards you. And if you look at this side, it will be moving away from you. And then this one on the lower left here is real. This is a picture of Centaurus A, which is the brightest radio source in the Centaurus constellation. It has this huge dust lane across it. This is actually not an accretion disk. This is a dust lane across the big optical galaxy, which is the white sort of fuzzy area here. So you don't see the center of the galaxy. It does have a supermassive black hole, and there is a jet you can see here coming out from the poles. Now, we actually see jets in quite a few sources out in the universe. And we can, theorists, of which I'm not one, figure out how you can generate these jets from the physics we know. And this is a simulation from Professor Proger, Daniel Proger, who's somebody I know, showing how you can generate a jet from an accretion disk with what he calls latitude-dependent angular momentum. So that means the speed that something's going around with depends on how high or low it is in the accretion disk, and a magnetic field, which will be radial. And as you can see, he's able to launch this jet here from the poles. Here's your little accretion disk down here. And it's fairly steady, but it's not smooth. It's not a smooth flow at all. You tend to get these bursts of material coming out at different times. And you'll see how that looks in real sources in a minute. So we do understand something about how to generate jets. So here's some more. We've actually been looking at jets in the radio for a very long time. Galaxies that are outside our Milky Way tend to have a lot of them have radio jets. And on the bottom right here is one called M87, which is fairly nearby, and it has a classic type of structure. The supermassive black hole is in the middle here, and there's a very bright core from the material around it. This jet is coming out in a direction fairly close to our line of sight. It's very narrow, and it has these bright spots as sort of clumps of material get emitted out along the poles from close to the black hole. At some point, this material will hit like a cold, dark cloud, which will slow it down. And what happens then is that the X-ray emitting plasma sort of spreads out into what we call a lobe. And you'll see there's a lobe on the other side. There's actually a jet on the other side, but we don't see it very well because it's pointed away from us. So it's much, much fainter. So actually, we generally only see one-sided jets, but we know they're both there. So this emission in these radio jets is not thermal, like your barbecue grill coal. It's what we call non-thermal emission. There's a magnetic field that's going out along this direction radially. And we have a plasma of ionized particles, so electrons. And the electrons spiral around the magnetic field. And as they do that, they emit photons of light that are fairly low energy. They're mostly in the radio. And these electrons actually moving quite quickly. They're what we call relativistic, close to the speed of light. So this is how the emission here is being generated. It's non-thermal emission. And we do also sometimes see optical, and as you'll see, sometimes X-ray from this as well. So this is Centaurus A again. This is a picture we looked at before, and it was a composite of observations from different wavelengths. So I just wanted to show you how different a source can look if you look in a different waveband. So in the middle here, we have the radio picture. I'm sorry it's a bit small, but you'll be able to see, similar to this, there's a bright source here, there's a jet, and then there's lobes above and below that are the end of those jets. In the optical, you see the white, sort of amorphous, it's an elliptical galaxy, it's not got much structure. But you also see this dust lane because you can't see through the dust lane, so you stop seeing the stars. So you know the dust is there, here. And then in the X-ray, this is what you see, a very complicated structure. You actually see X-ray, thermal X-rays, which are from very hot material. These are the red sort of amorphous emission here. You see the dust lane somewhat in the X-rays as well. You see a jet, and you also see X-rays from around where these lobes are. So there's a lot of different sources of X-ray emission in this particular source. So in order to get a complete picture of most of the sources out there, you need to look in very many different wavebands with different telescopes, some on the ground, some in space. So I'm now going to move up to the X-rays, and since I work for the Chandra X-ray Observatory, I'll advertise it a little bit. It's NASA's X-ray eye on the universe. It's a great observatory, and it's Hubble's X-ray sister. It was launched in 1999 on the shuttle Columbia, but it has an orbit that's much, much bigger than Hubble, so we can't go out and service it like the Hubble Space Telescope has been serviced. Hubble, by the way, looks in optical and UV light, so lower energy light than the X-rays. This orbit is about 3 days long, and it goes a third of the way to the moon. And we've been observing with it since 1999. It's observing as we speak, and it's still making exciting new discoveries. But I want to tell you the story of the actual first object we looked at in the sky, at least the first one we looked at on purpose. Now, as you know, when you look at anything with your camera, with binoculars, with a telescope, you have to focus that equipment before you can see a clear picture. And the same is true of a telescope, a big telescope, or even Chandra, a satellite telescope. So we decided we needed to look at a point source, because the sharper the thing you're looking at, the better your picture will be. Now, stars are good point sources. Even with the biggest telescopes, there's still dots of light. You can never see the size of a star. They're too small compared with the distance away. But stars are not very good X-ray sources. So we decided we had to look at a quasar, which, because the center is so bright, they tend to look like stars. They look like point sources if they're far enough away. And this is one with a name here, which indicates its coordinates. It's in the southern hemisphere, and it's at a large distance. It's about 3 gigaparsecs from us. And lo and behold, we looked at this star. I wasn't in the control room, thank goodness. We looked at this quasar, and found that instead of a point source, we had this little shadow on the side. And this is the X-ray picture here. This is actually a deeper X-ray picture than the first one, but there's a shadow on the side here. And they were very worried. There are 4 mirrors on Chandra. They thought perhaps one of the mirrors was misaligned or something, or perhaps something had got in the light path and was perhaps reflecting part of the light off to the side, and this would have been a major disaster. So all the engineers thought through the whole structure of the telescope to try to figure out what problem could be creating the picture we see. They came to the conclusion that nothing could do that, and it had to be real. And in fact, it is real. Now, we actually knew, this is a radio picture of this source, we knew it had a radio jet. It has a lobe here. This is the quasar itself, and this is a ATCA radio picture from Australia. Here's the jet on the right side. It actually has a bend in it here. So we knew it had a radio jet. However, in the optical, this is from the sky survey, there is no jet. It's just a point source. The size here is just the resolution of the telescope on that particular detector. These are just stars in our way, just along our line of sight. So we weren't expecting anything in the X-ray, but in fact what we see is this X-ray jet right on top of the radio jet. It's about 5 arc seconds long, which at that distance is 200,000 light years. So the theorists had to ask the question, how can we possibly have X-rays coming from a jet that is this long? The electrons would have to stay at so high velocities for such a long time to give you X-rays. And so the answer, and I should have told you actually, it's called synchrotron radiation, this non-thermal radiation that gives you the radio emission. And it can produce X-rays, but not usually over this large a distance. So the way it was figured out that this is happening is by what's called Compton scattering. You can actually get a photon that's been emitted by one of these electrons interacting with another of these electrons. The electrons are moving very fast, and they can give that photon a boost, and they can become X-ray energetic as X-ray photons. That's called Compton scattering. It can either be a photon that's already in this jet here. This is a schematic of the jet. Or it could be a photon from the cosmic microwave background, which is at the back, is everywhere. So there are photons there. So that's how we explain them. X-ray jets. And now it's a big industry to look at X-ray jets. This is a picture of a very big galaxy called M87, which is rather chaotic. And I'm looking into the center here, and I have jets, a jet in the middle, which is about 10% of the size. This is the radio jet, bright core, lots of knots. It's also a jet in the optical with Hubble Space Telescope. This is VLA, and Chandra. You can see the structure is somewhat different. So we can actually learn a lot about the physics by looking at the relative brightness of these different hotspots along the jet. Here are some more. I've got to go through these quickly because I'm running out of time. This is Cygnus A, a big radio source. This is the radio emission. Looks very like the last one I showed you. This is an X-ray jet in 3C273, which is the brightest quasar in the sky, near to us. That's the quasar itself. And this is a nearby source, which is very big, and the red shows the radio jets. The blue shows the X-rays. And in this case, these are thermal X-rays, and the radio is actually pushing holes in the X-ray emitting gas. So we see a lot of variety out there. One more final thing I'll go through quickly. As well as jets, we can also get material. This is another from Dan Proga, another model. We also get material that comes up off the accretion disk surface here. And then this X-ray source blows it away. So you get very high velocity gas, which we can't image because the region's too small, but we see absorption lines from that gas at very high velocities. So it's pretty chaotic around a black hole. And then finally, in order to introduce Francesca's topic, I'm going to talk just for a couple of minutes about how these supermassive black holes form and grow within the galaxy. I already talked about the fact that they form as the galaxy forms. They accrete in a secular way. That is, material within the galaxy just falls in. Even stars that get too close will fall in to the central black hole, and it'll grow. But they have to grow pretty fast because we have sources that are 10 to the 9, a billion times the mass of the sun at a long distance, when the universe was only 10% of its current age. So that might not be fast enough for some of them. Galaxies tend to form in groups. So if they're in groups, they can also accrete from intergalactic medium, sort of medium in between those galaxies. So that helps. And then also cosmological accretion can happen. The galaxies tend to form in what are called dark matter filaments. And dark matter filaments are how the universe is really grown. If you have a region of the universe which has more matter than anywhere else, it'll have a bigger gravitational force, so it'll tend to grow. So you end up with these regions that are more dense than anywhere else. That's where the galaxies form, and the black holes can accrete from the whole filament and grow quite fast. But the final way, and probably the way the biggest black holes grow, is through what we call major mergers. On the left here, I have a beautiful picture of two galaxies that are interacting. They're no longer two spiral galaxies. They now are being deformed by the gravitational force of the other galaxy. So this is one. And then here's another one that is already merged. And it looks pretty chaotic, but it's only a single galaxy now. When we looked at the middle of this, we actually saw two X-ray sources, which means we have two supermassive black holes in the middle. And they haven't yet merged. When they do merge, they'll get brighter and they'll blow a lot of this material away, and we'll have yet another quasar that's bigger. And here's a bunch of pictures of quasars that have quite chaotic material around them, so that the host galaxies are no longer spirals or ellipticals. They're what we call irregular. So with that, I'd like to hand over to Francesca, who will tell you much more about how galaxies merge and the black holes grow.
Belinda, thank you. Now, while we're setting up, everybody, bear with me. Stand up. You can do it. Take a deep breath. Stretch. Jump up and down 60 times. All right, stretch your legs. Take another breath. All right. Let's sit back down, and we'll complete our presentation tonight. I'm going to peek out very quickly to see what the sky looks like. Oh, can't believe it. It's beautiful. All right, Francesca, are you ready?
Yes, I think. Can you hear me? Yes, I hope so. Okay, so thank you, Belinda, for the nice explanation of how black holes look like and what are the properties of the supermassive black holes and how they form via accretion towards the accretion disk. But I will now take on from the last slide Belinda had, and I will talk you about the formation of the idea of the formation of supermassive black holes via galaxy-galaxy merging. And in particular, I will focus on a galaxy that which supermassive black hole has been kicked away from the center and is moving out from the galaxy itself. So, as Belinda said, one way of forming supermassive black hole is merging of big and luminous galaxies. And this is like a theory that has been going on in the last 5 to 10 years, and now theorists and modelists started to produce complicate theory about this supermassive black hole formation. And I like to think about it like a galaxy-galaxy dance. And I will show you a very short video of taken from a simulation where you can see the two galaxies approaching from far away, start to exchange gas and stars and material, and when the galaxy merge into a new galaxy, if we zoom in towards the center, what we can see here are the two supermassive black holes that were in the original two galaxies, and you can see that there is a black dot at the center and the accretion disk around, as Belinda was showing, and when the two supermassive black holes, they become closer and closer, they will start to rotate on a Keplerian orbit until when they are very close and rotate very fast, the magic happens and da-da, they merge into a new supermassive black hole. I know you are all looking at this, but I forgive you and I will ask questions afterward. What you saw at the end is like the new supermassive black hole that is being formed from the merging of the two parent supermassive black holes that were in the original two galaxies. And in the moment of the merging, there is a huge release of gravitational waves that here are represented in this simulation by a blue spiral around the supermassive black hole. This is not just a model, because now the observer, like me, we started to look out in the sky and look all the different galaxies going through the different steps of the galaxy-galaxy dance. So we now see many galaxies that are approaching one to the other, and the best example is our own Milky Way that we recently discovered that our Milky Way is moving towards the Andromeda galaxy, one of the other big galaxies in the local group. And in about 4 billion years, there will be a huge collision. And just to make it more complicated, also the Triangulum galaxy, M33, that is just a bit farther away, will join the party, and they will have a big dance all together. We now see more and more interacting galaxies, and this is not an easy task. The observer have been using a lot the Hubble Space Telescope. We see beautiful interacting galaxies. This is an image of the galaxy called the Mice that Belinda showed before. And what you can see here is that you can recognize still the two parent galaxies, this one and the other one, but you can clearly tell that they had already gone through a close-by a passage or an interaction, because you can see that there is some bridge here of material, like star and gas, that the two galaxies are exchanging. And the two galaxies, they have also big tidal tails, asymmetric. And these theories tell us that this is a clear signature of a recent interaction between the two. We move on. Then we see many galaxies that had recently emerged. And this is a little bit harder to tell and to establish the date of the recent merger. But they are observers working on galaxies. They are doing a very good job now. This is a beautiful example, NGC 6240, a little bit farther away than the Andromeda galaxy, 330 million light years away. And what you can see is that the galaxy has a very irregular shape, a lot of arms, and it's not really symmetric. And what you can see in the optical using the Hubble Space Telescope, you can see that there are a lot of regions with a lot of star formation going on. And this is a clear signature of a recent merger of two big galaxies. And when you look in the center and you zoom in, and you look at this galaxy with a Chandra X-ray telescope, so in the X-ray, as Belinda was telling before, you can see that at the center there are still the two supermassive black holes. So the two big galaxies already merged, but the two supermassive black holes at the center, they didn't merge yet, so they are rotating very fast, like in my video. Very fast, one around to the other, and soon they will merge too. So what happened next? After the merging of the two supermassive black holes, if you remember from my video, there is the magic moment. This is the magic moment of the emission of the gravitational waves. This emission of gravitational waves happen at the moment of the coalescence of the two supermassive black holes. This is really a technical word. So here at the center, there is only one supermassive black hole, and this one is as you can clearly understand, this is just an artistic representation of gravitational waves, because we haven't detected them yet, and we are not even close to. But we know that gravitational waves are produced in this moment of the merging of the supermassive black hole. They have been predicted by Albert Einstein, general relativity, and theories that are making simulations are now including, in numerical relativity simulation, are now including the part, the component of the gravitational waves emission. And I'm an observer, so I know nothing about theory. So I like to think about them like ripples in the fabric of the space. This is my romantic Italian view of gravitational waves. So the intensity of these you are wondering, I hope you are wondering, what is the intensity of these gravitational waves? So the intensity of the emission of the gravitational waves depends, guess on what? The two most basic properties of supermassive black holes. Massive black hole mass and black hole spin. Belinda told you before that these are the two most important properties. And in this the black hole mass ratio and the intensity and alignment of the spin of the two parent supermassive black holes are the parameters that play the major role on the intensity and on also the shape of the gravitational waves. In fact, the gravitational waves, they can be symmetric, like the one you saw in the video, a spiral, the blue spiral around the supermassive black hole. Think about, it's like throwing a stone in a pond, and what you see are like concentric circles that are moving out, and this is like the gravitational waves should look like. And in particular configuration of these two parameters, the emission gravitational wave can be asymmetric. And here, I think about it like the shape of a drop. So on one side, the gravitational waves are more powerful, and on the other side are less powerful. So what happened in the case of asymmetry? what happened to the newly formed supermassive black hole in this case, that the black hole is kicked on one side of the galaxy, while in the other case, the black hole just stays at the center of the galaxy, and all the gravitational waves generates around. In this case, the black hole is kicked away from the center of the galaxy. So the kick velocity can be higher, can be lower, and this depends from the asymmetry of the original asymmetry of the gravitational waves. If the kick velocity is low, what will happen is that the supermassive black hole will be slightly displaced from the center of the galaxy and will start to rotate around the center of the galaxy. And at some point, will not take longer, like a couple of billion years, the supermassive black hole will fall again at the center of the galaxy. And this is what happened in most of the cases, more than 50%. I throw there a number, but it might be higher. And as you can understand, this is very hard to detect, because if the black hole doesn't reach a very large separation from the center of the galaxy, we will not be able to distinguish the light coming from the supermassive black hole, or better, from the accretion disk, as Belinda said, from the light of the center of the galaxy. When the kick velocity is high, what will happen is that the black hole can be completely ejected far away from the galaxy, like in this artistic impression. And as you can, so this is like a very rare case, so it doesn't happen many times. But in principle, this is much easier to detect, because if the black holes reach a very high separation from the galaxy, we'll be able to see the galaxy and the supermassive black hole somewhere far away, more or less far away from the galaxy. However, you can understand that if the black hole is kicked with a very high velocity, it will not be able to carry a lot of material. Think about you that leaving the house. If you have to rush leaving the house very, very fast because someone called you and asked, come out, you will not be able to pack a lot of stuff with you, maybe just the cell phone. Instead, if you are planning to have, you're moving, and you will take it with you will be easy, and you will pack all your stuff, and the movers will come. So you will be able to take very slowly all your stuff with you. And this is for the supermassive black hole. If the supermassive black hole is kicked very fast away from the galaxy, it will not be able to carry a lot of material, so it will not shine in the universe for a very long time. Instead, if the velocity is slightly lower, the black hole will have a lot of material, so we can see a supermassive black hole alone in the universe, but still shining for some time. So in both cases, these objects are really, as I told you, they are really rare, and most important, they are not really easy to detect. So, but maybe we want to find one. It would be cool if we could see one in the universe. So let's try to find one of these objects in the sky. And the best way to find this kind of object is to look at the big area of the sky with your preferred telescope. Mine is the Hubble Space Telescope, and then the Chandra X-ray Telescope. Let's look at this big area of the sky, and let's see if we can find one of these objects. When we look at big area of the sky, we call it survey, extragalactic survey. Extragalactic because we are looking outside of our galaxy, and survey because we are looking at the big area of the sky. And this is my survey, not mine, but I'm a collaborator of this project. It's called Cosmos, and this is a project that has been going on for the last 10 years, and I joined during my PhD. And as you can see, it's a big field. It started as a Hubble Space Telescope project, and this is the mosaic of the images taken with the Hubble Space Telescope. And this is a mosaic of more than 500 images from the Hubble Space Telescope. So you can tell that the images from the Hubble Space Telescope are really tiny in this field. And here, just to have a comparison of the size of this field, I put the moon. So is there someone of you that knows how big is the diameter of the moon projected on the sky? No? Volunteer? How much? No. No one? Okay, that's it. You ruined my story. I had a nice story, like, let's do it again anyway. So, oh, I have a dime here in my pocket. So if you take a dime and you go outside, I can tell you that you can put the dime and cover the whole moon with the dime. So you can measure the moon just putting a dime up there. And the size, the angular diameter of the projected angular diameter of the moon and the sky is half a square degree, more or less, half a square degree. So you can tell that this field is like a little bit more than 1 square degree on a side, and the total area is 2 square degree. So if we take now an area that is more or less the size of the moon at the center of this field, so how many galaxies do you think we have there? Numbers, please. 10, I don't know. 200. Millions. Sorry? 10,000. So the actual number, if we zoom in, and this is the real image of that square, we have about 500,000 galaxies. But these are not just out there. This is the number of galaxies that we can observe in that area from the epoch that we are now to the epoch at which the universe was about 2-3 giga-years old. So we also go deep back in time in the universe. So here we have about 500,000 galaxies. And how many of these do you think we can, in how many of these galaxies do you think we can observe one of these kicked supermassive black holes? Numbers. 10. Well, the correct number is maybe 1. Okay, maybe. So we didn't observe our cosmos field just with the Hubble Space Telescope, and this is an image from the Japanese Subaru telescope. We also observed this field at other wavelengths, because only observing a different wavelength, you can fully characterize your source in the sky, your galaxies. And Belinda said this before, and I will show you again another view graph about this concept, because I think it's really important to understand why we have so many telescopes and satellites out there to observe our sky. So this is an image of the sky in the optical band, like taken by Hubble, but it's the same way you go outside and you look at the sky. This is the same thing you could see. So here you mainly see stars. If you look in the infrared bands, and this is the image taken with the Spitzer satellite of the same galaxy, what you see in the image in the infrared are cooler parts of the galaxy. And in the galaxy far away, the main emitters in the infrared are dust grains that are heated by starlight, so by the stars that we see in the optical. And then if you look at higher energy, so much powerful sources in the X-ray, with the Chandra X-ray telescope, for example, and as Belinda said, looking in the X-ray is like taking X-rays of our body. In the X-ray band, you can see very powerful sources, like supermassive black holes, and also for close-by galaxy, X-ray binaries, so small supermassive black hole. And here you can see in this galaxy, we see the supermassive black hole at the center, and a lot of X-ray binaries around. And only when you put everything together, you can have a clear, complete picture of the galaxy. And only putting the 3 bands together, you will be able to understand what you're looking at. So what we did for our Cosmos survey, we look at the field in the infrared, in the radio band, in the optical, in the near infrared, and we also look at it in the X-ray with the Chandra X-ray telescope. And this is the composite image of the inner part of the cosmos field. And as you can see, I just want to remind you what we were looking in the optical. So this is the optical image of the same field, and this is what we look in the X-ray. In the X-ray, we see not as many sources as in the optical, because what we see in the X-ray are the active supermassive black holes at the center of all those galaxies. And here we have about 2,000 X-ray sources. So the source that I will talk about in the next few slides is this one, little white dot, like meaningless, if you look at it like that in the X-ray. But when you look at the Hubble image of the source, it's amazing. Like every time I look, this one is my preferred galaxy. And so when I look at it, I'm just in love as the first day. And the name of this object is CID42, and has been observed in the cosmos field. What you can see in this Hubble image of CID42, you can see a very beautiful, big tidal tail. And tidal tail, as I told you before, are a clear signature of a recent merger, right? And if you squeeze your eyes, and if I move the arrow, and if you squeeze your eyes and you look at this side of the galaxy, you can tell that there is another tail that is smaller than the other one, or maybe we cannot fully see the other tail because of the projection of the galaxy in the sky. And just to give you an idea, the size of this galaxy is like 1/50th of the size of the moon, so very, very small compared to the moon that I was showing before. What we see in the center of this beautiful CAD42, we see two optical sources, very bright. To Lou, they look similar, I guess, but to me, that I study them a lot, they look quite different. So what we discovered about these two optical sources is that this one, the one at the bottom, this one is the active supermassive black hole in the system. So it's a 10 to the 8 solar masses, so very big supermassive black hole. And we could tell that this is the supermassive black hole in the system because, again, we use X-ray data from the Chandra X-ray telescope. And this is a kind of a technical image. Here you're looking at the optical image on the background with on top the contours, these ISO density lines of the X-ray emission. So what you can see is that the X-ray emission, that is the unambiguous signal of the presence of an active supermassive black hole, is coming only from that bottom source. So what is the other source? The other source, after many studies that we have been done in the last 2 years on this object, we can now tell that this source is a very dense regions of stars and gas where more stars are forming. So we didn't stop. We took more data of this CAD42, my preferred galaxy, and we now use some ground-based facility. We use the Magellan telescope, thanks to the time that is available here at the Smithsonian Astrophysical Observatory. We use the very large telescope that is a European set of telescopes in Chile, thanks to some friends that we have in Europe, as you can tell from my accent. And we also use the Keck telescope on top of Mauna Kea in Hawaii. So what we could get using these three different telescopes is that this source, the one that is the supermassive black hole in the system, this one, is moving away from the galaxy at a velocity of about 3 million miles per hour, so very, very fast. So what is going on in this system is that the supermassive black hole there is leaving the galaxy at a very high velocity and never coming back, I can tell. And the other source is the center of the galaxy. So what happened here, we had the merging between two galaxies, then there is, boom, the smash of the two galaxies, the supermassive black hole at the center, they merge, a huge release of gravitational waves, and for some reasons, the emission of gravitational wave was so asymmetric that the black hole has been kicked away at this very high velocity. And now, as the last slide, I will show, and this is the artistic impression of this source. You can see that the supermassive black hole, black at the center, with the accretion disk, is now leaving the galaxy and leaving a big black hole in the heart. Well, I didn't want to say black hole, a big empty hole at the center of the galaxy. So I will then finish showing the simulation that we have done to reproduce the dance of my preferred galaxy CAD42. And this is a work that I've done here with a Harvard grad student. And we are starting from the two parent galaxies of CAD42. And with at the center, the two supermassive black holes that here are white, I'm sorry. The two galaxies are the first interaction, exchanging some stars and gas and material. The two supermassive black holes at the center. Galaxies are coming back, start to exchange more material, and then they merge. And the two supermassive black holes merge, and the newly formed one is ejected away, like in CAD42, at a very high velocity. And as you can see, I can play it again, because this is too fast. And so again, the two supermassive black holes. And as you will see, at some point the image freezes, and at the moment where the supermassive black hole is the same distance of the one in CAD42, the image will freeze and will superimpose the real image of CAD42 on top of the one of the simulation. Here it is. So you can clearly see the same feature. And then the supermassive black hole will go away from the galaxy. And now we still see the supermassive black hole shining, but at some point when it will be far away, it will not shine anymore. And this is, as Belinda was saying, maybe there are a lot of dark supermassive black holes out there in the universe that we can see. So I hope you had fun, and I think we are done.